attached to a central tendon. With the parallel muscles, the tendons are at the very end. With the pennate muscle, the tendon is as long as the muscle is. It extends the entire distance. And then attached to the central tendon are muscle fibers running at an oblique angle. And if there's one central tendon with fibers on one side, it's unipennate. Extensor digitorum longus is unipennate. If you add another layer on the other side, running in the opposite direction, that's bipennate. Rectus femoris is a bipennate muscle. Central tendon, fascicles on both sides, running at an angle. And then if you take two or more unipennates or two or more bipennates and combine them, you have multipennate. Deltoid is multipennate. Here's 1, 2, 3 bipennates all joined together, collectively multipennate. So the deltoid is both multipennate and convergent. Pectoralis major is only convergent. There is no central tendon. All the fibers go from that broad origin to that point of an insertion. And then circular muscles. They function as sphincters because when they contract, they close up. The diameter decreases. The external anal sphincter muscle, the external urethral sphincter muscle. Those are both circular muscles, guarding the exits of the urinary and digestive system. As far as force production, you get more force out of the pennate orientation versus having the tendons just at the end of the muscle and the muscle belly shortening and pulling on the tendons. If you have all of these individual fibers pulling on the tendon at an angle, you get more force. And I'll try to explain this. Sometimes it works, sometimes it doesn't. So if I have two muscles of equal size, and already I've screwed up, this one looks smaller to me, and I can only fit so many muscle fibers in here. I'm limited as far as force production by the number of muscle fibers attached to the tendon and pulling on that tendon. If I made the muscle longer, by extending the length of these fibers, would this muscle be any stronger? No. What would it do better though? It would move body parts, bones, over a longer distance. In other words, you get a bigger range of motion. And that is the benefit of parallel muscles, whether it's strap-like or fusiform. They shorten a long distance. They move those tendons pretty close together. They give you a big range of motion. Shortening is really what they're designed for. So it doesn't matter how long the muscle fiber is. What matters is how many you have attached to the tendons. What if I took the same volume of muscle fibers and I broke it up into smaller pieces? So now instead of 10 really long muscle fibers, I have 10, 20, 30, 40, 50, 60 small ones. And I'm going to take all of those and attach them all to a central tendon. So all 60 are attached to this tendon. So I'm making basically a unipennate muscle. And comparing that to a fusiform of equal size. Which one is stronger? I've got 60 muscle fibers, all pulling on this tendon. Here I've got 10 muscle fibers pulling on these tendons. 60 is going to produce more force than 10. Doesn't matter how long they are. How long they are just determines how much shortening you get, how much distance you shorten. But force depends on how many are actively pulling on that tendon. Does that make sense? An analogy. I want to pull on a rope like tug of war. Let's say I pull on the rope and with this hand, and then you're grabbing my hand, and the person next to you, and the person next to you, and there's 10 of us in a chain. And we're all pulling together on this rope. Are we really 10 people pulling on that rope? One. It's really just one person, and you're limited by the strength of the weakest person in that chain. So how could we apply a lot more force to that rope instead of forming a long chain? With me, the only one actually pulling on it. Get 10 people all pulling on the rope. Each one, is relatively short compared to the chain of 10, but all of us are applying force directly on that rope instead of pulling on each other. Does that kind of work? So, deltoid muscle, which is relatively small, produces a ton of force. And there's a very important factor I'm leaving out, which has to do with biomechanics. Where the muscle attaches makes a big difference. So if the muscle attaches really close to the fulcrum, the point of movement, it's really hard to move that limb. Think about a shovel. If your hands are at the very end of that shovel, and it's way down there and you want to dig dirt, you're really far from the fulcrum. How do you get more power and lift a bigger load of dirt? You scoot your hands down and you get as close to that, the plate, as you can. So how the muscle attaches to the bone makes a huge difference. The deltoid muscle probably wouldn't have to be multipennate if it inserted somewhere lower on the lower arm, further away from the fulcrum, so you had a longer force on it. Instead, you have a really short force on it, but a really strong muscle. If you're interested in that biomechanics stuff, it's in Chapter 10. And they talk about first, second, and third degree levers. Which ones give you a mechanical advantage, which ones are at a mechanical disadvantage, the pros and cons. You need that extra bit of information to fully make sense of why we have multipennate, bipennate, and where you find them. All right, so to learn that muscle list, names, origin, insertion, action, and innervation. Models, PAL 3.0, which has models in it. Has anyone used PAL yet? Have you noticed that the models in PAL are similar or sometimes identical to what we have? All of the figures that are posted, there's labeled and unlabeled versions for you to practice labeling. And then the Mastering A&P study area has lots of labeling activities, including the ones in the Mastering assignment.
Is there any way to use the program without using Shockwave?
Not that I know of. And that seems to be interfering for a lot of people.
Yeah.
My only advice is, if you've turned off your pop-up blocker, and you've deactivated your virus protection program, which I know is risky when you're online, but just try it to see if that's the issue, and you still can't download, install, and use the plugins like Adobe Flash or Shockwave, try a different computer.
It just says that.
First, try different browsers. If it's not working on IE, try Mozilla. If that's not working, try Chrome. And pop-up blockers off and disable your McAfee or Norton or whatever you're using. Now, if you're really computer savvy, instead of actually deactivating your protection program, you go inside and you make allowances for certain websites. You make rules that say anything from this website is okay. But if you don't know how to do all that, just to see if that is the problem, turn it off.
For Macs, I think like this.
And Macs, I know nothing.
Yeah.
I'm PC. Sorry, not helpful. But I even tried it on my laptop and I had issues, and I never did in the past, but something with the new Physio X. But then I got onto my office computer and it was just fine. So, you know, if you have a laptop and that doesn't work, try your desktop. If that doesn't work, try the computer lab in the library or the LRC. Hopefully it works somewhere. Everybody's been turning in Physio X, so I'm assuming you have found a way to get that to work.
Is it just mastering? Because I use my Mac and I don't have any problems on any of them.
There's a certain operating system version that Shockwave supports.
Some of this we can answer now. What is the origin and insertion of biceps brachii? Even if you don't know the bone marking, you can be general and just give me the bone. Origin. Scapula. Insertion. Radius. How about bone markings? What part of the radius?
Radial tuberosity.
Radial tuberosity. What part of the scapula? Supraglenoid tubercle, which is this little bump on the rim of the glenoid fossa at the very top. And what's that little finger-like projection that comes out of the coracoid process? What joint does this muscle cross? Biceps brachii. It does technically cross the glenohumeral joint, and so it can produce slight flexion at the elbow, but that's not its main job, even close. It completely crosses the elbow, and that's its job, to generate movement at the elbow. And what's that movement called? Flexion. What is the primary antagonist of biceps brachii? Triceps brachii. Name one synergist of biceps brachii. They all start with B. Brachioradialis and brachialis. What is the muscle fiber arrangement of biceps brachii? Parallel, convergent, circular, pennate. Parallel. Fusiform or strap-like? Fusiform. You can take a stab at this last one. Which single muscle can flex, externally rotate the thigh plus flex the knee, resulting in a cross-legged position? I have to make that crisscross applesauce. I'm outdated. Indian style's not PC anymore. Sartorius. Sartorius crosses the hip joint and the knee joint. Chapter 8. I'm going to start with some recap, some stuff that we covered in Chapter 8, Part 1. Here. So we are focusing on synovial joints only now. Factors influencing the stability of synovial joints. The fit or the shape of the articulating surfaces. The better the fit, the less range of motion, but more stability. Perfect example is your two ball and socket joints. acetabulum is more of a cavity, and the head of the femur fits in there. The glenoid fossa, aka glenoid cavity, but fossa is a better term, is more like this. So while the acetabulum kind of envelops the head of the femur, something has to hold the head of the humerus against the glenoid cavity. It's a very poor fit. Something round against something straight or flat is a very poor fit. Now both of these joints have a rim of fibrocartilage that does improve the articular fit a little bit. It's called a labrum. So there's a labrum in the acetabulum, and there's a labrum in the glenoid cavity. It deepens the cavity a little bit, improves the fit a little bit, but the whole reason you have a poor fit with the shoulder is so that you have more range of motion. And the reason why you have a better fit in the hip is so that you have more stability. Which of those is more weight-bearing? The hip. There's larger forces applied to the hip. You don't want those bones to dislocate. It makes sense that it's more stable. And to do all the things that we can do at the shoulder joint, which is pretty much move in any direction, you're going to have to sacrifice stability. Ligaments add stability by reinforcing the joint capsule, and I talked about these last time. If the ligament is inside of the synovial cavity, it's an intracapsular ligament. If it's outside of the synovial joint, extracapsular ligament. If it's actually within the joint capsule, which means a thickening of the fibrous joint capsule, it is a capsular ligament. Muscle tone is also a factor affecting stability. Most important for highly mobile joints such as the ball and socket joints. So muscles that cross the hip and muscles that cross the shoulder help stabilize those joints and keep the heads of the humerus and femur pushed up against those cavities, acetabulum and glenoid cavity. What's the name of the group of muscles that provides a lot of support for the shoulder joint? There's 4 of them. The acronym is SITS, S-I-T-S. Each letter refers to the first letter of the name of each of those 4 muscles. I'll give you the first 2. S of sits, supraspinatus. I of sits is infraspinatus. Here they are. What are they called collectively? Because they form a cuff.
Rotator cuff.
Rotator cuff muscles. They form a cuff around the head of the humerus. Rotator because their other job, main job is stability, their other job is rotation. They can rotate. External or internal rotation. Which is why if your physical therapist is giving you exercise to strengthen those muscles because you're having some issues with your shoulder joint, they will ask you to take a elastic band and do some internal and external rotation exercises. Movements allowed by synovial joints. These we talked about last time as well. So you have the y-axis. When you rotate around it, you move through the transverse plane. Z-axis, when you rotate around it, you move through the frontal plane. X-axis, when you move around it, you're moving through the sagittal plane. Different synovial joints provide movement through 1, 2, or all 3 of these planes, or in some cases, through a plane but not around an axis. So if you can move around 1 axis, uniaxial joint, 2, biaxial joint, 3, multi. If you can't move around an axis, but just glide through a plane, which is where you have gliding or planar joints, that's non-axial movement. So the only four you needed to know, and you still do: elbow, knee, which are hinge joints, uniaxial; shoulder, hip, which are ball and socket, multi-axial. Types of movements at synovial joints. I'll act these out for you. And I do have slides as well. I guess I should act them out up here so I can flip through the slides. Flexion. Right, so each of these has a definition, but you should also know what the movement looks like. Movement around the x-axis through the sagittal plane, reducing the joint angle. The joint angle is anatomical position. So this is the angle of my elbow joint, 180 degrees, anatomical position. To reduce that angle, I bring the forearm towards the arm. Flexion. Once you have flexed, the return to anatomical position is extension. Or you could say an increase in the joint angle as you move around the x-axis. So flexion at the shoulder looks like this. Flexion at the elbow, like this. Flexion of the spine, or vertebral column or trunk. Flexion at the neck. Flexion at the wrist. Flexion at the knee. Flexion at the hip. Extension, the return from flexion, increasing the joint angle. So the opposite of everything I showed you. If you start flexed, here's extension at the neck. Flexed at the spine, here's extension at the spine. And if you go beyond anatomical, hyperextension. Not all joints that flex can hyperextend, but they can all extend back to anatomical. Knee, so if I'm flexed, and then I bring my leg back down, that's knee extension. If my thigh is up and I have flexed at the hip, bringing it back down, extension. But I can go further, right? I can come down, and then I can keep going. So that's hyperextension at the hip. Can't hyperextend at the knee or the elbow, but you can hyperextend at the hip and shoulder. Shoulder flexion, shoulder extension, shoulder hyperextension.
If you have an injury, it could be the hyperextension of the knee or elbow, right?
Mm-hmm. Abduction. Movement around the z-axis, through the frontal plane, away from the midline. So my hinge joints can't move around the z. Ball and sockets can't. Spine can't. So at the shoulder, abduction, and then the return to anatomical adduction. And at the hip, abduction, adduction. Fingers, abduction, adduction. What else can you do? I think that's it. Circumduction. It's a combination of flexion, extension, abduction, adduction.